In this module, I'll complete the remaining part of the numerical optimization technique. Mainly I'll discuss about the Newton method and quasi-Newton methods. The Newton method, first I'll start with the programming. Purely I'll program the Newton methods in R, and using very simple function, and then I'll show you some inbuilt functions in R, like the NLM package and max like package, where max inner is the function that you can use, and also in NLM you can use the NLM function to optimize any function by the Newton methods. And then I'll show you how to implement the quasi-Newton method in R. It's not much of programming here, because there's an existing function called optim, is a very strong function that can optimize different any function by different methods. So one of the methods is the quasi-Newton's method that we can use. We can use the optim function to get the estimate by quasi-Newton methods. And I'll leave with the trust region methods with some references. Won't discuss much over here. As I told, in this second module of numerical optimization, we'll see how to implement the Newton methods and quasi-Newton methods in R. Initially I'll start with the Newton's method, implementation of Newton's method in R. So the Newton methods is an iterative root finding algorithm where we start with an initial guess x0, like gradient descent method, and each successive guess is defined using the iterative process as xn plus 1 is equals to xn minus fxn divided by f prime xn. Here is a simple implementation of this in R. See, I define a function called Newton as follows. The arguments are f, the function, the TOL, that the accuracy that you need, that is 10 to the power minus 12, and x naught equals to 1, n equals to 20, that fixed up. That means even if you don't pass any values of these three arguments, by default it will take, the total will be taken as 10 to the power minus 12, x naught is 1 and n equals to 20, but if you want you can change the values. And then we define a variable h equals to 0.001, xi equals to 1, x1 equals to say x naught, and p equals to numeric of n, and while I less than equals to n, the use the while loop, and it will run till I less than equals to n. And then df dx, the first derivative of the function, is just that ad hoc very the earlier definition of calculus of our textbook, that we know that f x naught plus h minus f x naught by h. So h, that already I defined as 0.001. So this very crude method, though, just for implementation purpose I am doing like this. So x1 is equals to then x naught minus f x naught divided by df dx, and then pi equals to x1, then again I equals to I plus 1, and if absolute difference between x1 and x naught less than TOL, then breaks, and x naught equals to, otherwise x naught equals to x1, and then finally close the while loop and return p1 to I minus 1, and that will give you the all sequence of the results of the full iterations step by step. The step size of numerical differentiation is hard coded to be 0.001. This is arbitrary and should probably be a parameter, and the algorithm will run until either the number of steps n has been reached, or the error of tolerance, say x1 plus xn plus 1 minus xn less than epsilon, where epsilon is defined as the tolerance parameter, that is total. The function return a vector of iterated x positions which will be less than equals to n. Here is a simple example. For instance, to find the zeros of a function, say f(x) x to the power 3 plus 4x square minus 10, which in R we can represent as f function of x x cube plus 4x square minus 10. This is a function that I define, will return the value of the fx function that is there. And let us plot the function as follows. So, carve f from 1 to 2 and abline h equals to 0, and so you can, a curve will give the plot and abline will give the horizontal line at 0. So, it seems obvious from the plot that the 0 of fx is the range between 1 to 2 is somewhere between 1.3 and between 1.3, yes, 1.3 and 1.4. From the plot it is clear. So, this is made even more clear if we tabulate x, y values over this range. So, there is x equals to sequence 1 to 2 by 0.1, we get the sequence incremented by 0.1, and then x, y equals to c wine x fx, and print the x, y, then you will get these values, and it is clear that it is between 1.3 to 1.4 somewhere here, because for 1.3 it is minus and for 1.4 it is positive. So, the 0 of the function must be lying in between 1.3 to 1.4. So, Newton's method, using the function defined earlier, we can run the root finding algorithm. The p equals to Newton if x naught equals to 1, the initial value, and n equals to 10. So, the default values are there, I have specified on my own, and then if you run that Newton function, you will get the p, and p is telling 1.4, then 1.36, 1.36, 1.36, 1.36, 5, 2. So, now it converts to 1.36523, 0. You can stop the iteration here and return the value 1.365230 as a root of fx, and plotting the last value in the iteration, say the curve fx from 1 to 2 and abline h equals to 0 is the earlier plot, and we are adding a new line, abline v, the vertical line v, p length of p, and that will give the actual solution. The intersection point between the 0 line and 0 horizontal line and the vertical line, another vertical line at this p, the 1.365230 point will give you the actual solution. So, the abscissa is 1.36523. In the iteration loop, we use the school book style numeric derivations as dy dx fx plus fx by epsilon, and epsilon should be tends to 0 actually. So, it also worth noting that R has some support of symbolic derivations. So, we could use the symbolic functions expressions as follows. A simple example of symbolic differentiation in R is as E expression. So, everything, the differentiation should be within expression. So, we have to convert that function as an expression. So, I am converting that function as an expression sin x by 2 into cos x by 4, and then we are calculating dy by dx. So, within capital D you pass the first argument as that expression, and second argument within double quote the differentiation with respect to x. So, you put x over here and the result will be given here. If you just type dy dx, you will get cos x by 2 into half plus cos x by 4 minus sin x by 2 into sin x by 4 into 1 by 4, the derivation of that expression. In order for these to use full, obviously we need to be able to evaluate the calculated derivations. We can do this using eval method, eval function. So, say z equals sequence from -1 to 1 incremented by 0.1, and eval function we can use eval dy dx and then list x equals to z. So you have to pass x equals to z by the list, the sequence, and that will evaluate the differentiation. So now we will see the different especially the two different inbuilt function that actually solve the any function by Newton method. So NLM provides a Newton algorithm, the max-like package for maximization of likelihood function. This package includes the Newton-Raphson method, that is Newton-Raphson in SPU-RS package also provide this Newton-Raphson one function. So NLM provides the Newton algorithm, max-like also give the Newton algorithm, that is this Newton-Raphson from the SPU-RS package also provide the Newton methods. Let us start with NLM. In NLM, suppose we have to solve the following system of equation. So minus 400 x1 into x2 minus x1 square minus 2 into 1 minus x1 equals to 0, and 200 into x2 minus x1 square equals to 0. So fg equals to function of x. Well, first we define that function. Fg is function of x, that is the gradient would be it should be passed in two array. So I mean array of 2, that is gr is function of x1 and x2, and then the first term can be written as minus c of minus 400 into x1 into x2 minus x1 square minus 2 into 1 minus x1, and the second term is 200 into x2 minus x1 square, and that is the gradient function and within the fg function. And then x1 equals to say x of 1 for the first position of that array, and x2 is the second position of the array, and then res equals to 100 into x2 minus x1 square whole square plus 1 minus x1 whole square, and attribute rs is the gradient gr x2. So if you pass x1 and x2, you will get the gradient value, and we will attach the attribute in this manner and return res. So that is the fx function return, and that function can pass through the NLM function, and NLM function, say NLM fg starting point is minus 1.2 and 1, the Hessian matrix equals to true, then it will give you the minimum is 1.18 into 10 to the power minus 20, the difference, the estimate is 1, the gradient are given this, the Hessian also provided in this manner, the code, and the number of iteration was 24. So another function, that is max inner. So max inner can be the max like from max inner package. So estimate the exponential, say take this example of exponential distribution parameter by MLE. Say library max link t equals to REXP 100, 2 parameter is 2, say, then log likelihood is function theta sum of log theta minus theta into t. Note the log likelihood and the gradient are summed over observations. So gradient likelihood is function theta sum of 1 by theta minus 1, and Hessian likelihood or Hessian of the likelihood coming around function of theta minus 100 divided by theta square. So estimate the finite difference gradient and Hessian. So now in max inner package we will pass the log likelihood, then start equals to 1, control list print level equals to 2, and that will give you the final results as 1.75977, and functional value is minus 43.48379. A gradient also close to 0, and 5 iterations was done. The summary is that Newton-Raphson mean maximization, number of iteration equals to 5, return code 1, gradient close to 0, functional value is minus 43.48, the estimate is 1.75, and the gradient is 2.84 into 10 to the power minus 8. You would probably refer 1 by mt instead. So estimate with analytical gradient and Hessian So again, max NR is log likelihood, gradient of likelihood, then Hessian of likelihood, and start equals to 1, then summary of A, that will give you the estimate 1.75977 and into 1.21 into 10 to the power minus 10. So another function, that is Newton Raphson from SPOO-RS package. Just install the SPOO-RS package and load it, and define this function of the first one is the function, then the derivative all together would be written by the function. So pass the argument x, then fx is log x minus exponential of minus x, and dfx is 1 by x plus exponential of minus x, and return is cfx dfx, that is the function of the user defined function of the following mathematical function. And then we will pass that function Newton Raphson ftn4, then parameter 2, and the difference that we need is 10 to the power minus 6, and then after the fourth iteration you will get it converts, and the result is 1.3098. Next we will move to the quasi-Newton method. The quasi-Newton method is basically from an initial guess x naught and a approximate Hessian matrix B naught. The following steps are repeated as xk converges to the solution. So obtain a direction pk by solving bk pk minus delta fxk. Perform the line search to find the acceptable step size alpha k in the direction found in the first step, then update xk plus 1 equals to xk plus alpha k pk. Set xk equals to alpha k pk, then yk equals to delta f xk plus 1 minus delta fk, and bk plus 1 equals to bk plus yk prime by yk prime xk minus bk xk sk prime bk divided by sk prime bk sk, and fx denotes the objective function to be minimized. The convergence can be checked by observing the norm of the gradient, that is the modulus of delta fx1. Particularly beta naught can be initialized with beta naught equals to I, so that the first step will be equivalent to the gradient descent, but further steps are more and more refined by bk, the approximation to the Hessian. And the functions, here we define a functions func c as x and out equals to x1 minus x2 whole square plus x2 minus x1 whole square, and return is out. And then we will use the function optim, where parameter equals to 0 0 initial value, fn is function func c, the gradient null, method bfgs, which is the Newton Raphson the quasi-Newton method, that is Beroiden, Fletcher, Goldfarb, Shannon, that is BFGS algorithm. So this algorithm is actually the quasi-Newton algorithm in optim function. You can choose that BFGS, and you can define the lower is minus infinity, upper is plus infinity, and then you will get the actual estimate of the variable, the results. And the optim, this way you can also use the L minus L hyphen BFGS hyphen B method. That method, this is actually Beard et al 1995, which also box constraint allows the box constraints, that is each variable can be given a lower and upper bound. Other methods that optim supports. The default method of in optim is an implementation of the Nelder and Mead 1965 that use the function values and is robust but relatively slow. It will work reasonably well for non-differential function. The method CG is actually conjugate gradient method. Based on that, the Fletcher and Reeves 1964, but with the option to Pollack, Riviere and Bell, Sorenson updates. The conjugate gradient method will generally be more fragile than BFGS method, but as they do not store a matrix, they may be successful in such larger optimization problem. The final method is trust regression method, though I don't discuss much here, but I'll give some reference where you can get sufficient documentation for further knowledge. For optimization by trust region method, I would like to refer the trust package and the vignette on it. You can get the vignette through these locations. The details of the trust is in this location. You just click over there, you will go enter into that website and get this PDF file. So PDF file give you all the details of implication of trust region method in R. Hope that will help to understand or learn the trust region method. I am not discussing much over here. So that's all about the numerical optimization methods. I split it into two modules. Mainly I focused on the line search. In this second module of numerical optimization, we have learned mainly two methods. One is the Newton method, another is the quasi-Newton methods, and we implemented both the methods in R. Even also we learned for the Newton method some existing inbuilt functions, that how it can be used to optimize based on that particular method, Newton methods. And I feel after completion of this module, anybody can implement any kind of function to estimate the parameter by any three of the main methods that we have learned in this numerical optimization technique.